Today we will start looking at droplet burning. Now the context of droplet burning comes up in many liquid fuel applications. Many of the popular liquid or commonly encountered liquid fuel combustion applications is in automobile engines, where we inject either petrol or gasoline, as it is called in different countries, or diesel in piston engines, or for example some form of kerosene in aircraft engines and so on. In all these things, the fuel is essentially in the liquid form, and it is atomized into a spray, and the spray is essentially composed of a ensemble of lots of different droplets of different sizes. Another application of droplet combustion is in liquid rockets, where you typically are injecting a liquid fuel as well as liquid oxidizer, and you try to atomize both of them and to try to burn them. So in this situation, then in general what basically happens is whichever is in liquid form has to evaporate and burn in the gas phase, and the combustion that is occurring in the gas phase has to feed back heat to the liquid fuel or oxidizer in order for it to vaporize. In the case of liquid rockets, where you have both liquid fuel and liquid oxidizer having to be atomized into sprays, and the sprays have to mix and vaporize and burn together, you have a problem of multiple droplets of different species which are trying to vaporize based on flames that are existing, while the gas phase products of these, or gas phase vapors of these, are mixing and burning. And that's a little bit more difficult problem to think about. An easier problem is where you are looking at a fuel being in liquid phase and being atomized into spray and burning in a gaseous oxidizing ambience, right. So first of all, we will try to limit ourselves to this situation where only one of the reactants, namely the fuel, is in liquid phase, and it vaporizes, and its vapors mix with a gaseous oxidizing ambience, right. So that's the first limitation that we will set for ourselves. The second thing is we will not deal with sprays now. We will deal with a single droplet, so out of the spray, and whatever is the fate of the single droplet is something that we should expect for all the droplets to face in a ensemble of them that's constituting the spray, if the spray is a dilute, what's called as a dilute spray. So what is meant by a dilute spray is that the spray droplets are not interacting with each other. In other words, the combustion that is occurring in one droplet doesn't influence the vaporization of another droplet that is nearby, and so on. This is typically what is called as a dilute spray, and many times you don't necessarily have a dilute spray at all. You have typically what's called as dense sprays, where most of the combustion happens in droplet clouds as opposed to happening on single droplets. But for the sake of convenience at the moment, we will try to analyze a single fuel droplet burning in a gaseous oxidizing ambience. So this is the framework in which we want to do this. Having said that, then we want to look at this essentially in the context of diffusion flames. Basically, a droplet combustion essentially is fundamentally a diffusion flame, because you are talking about a fuel that is vaporizing and the vapors are mixing into the gaseous ambience just at the flame. Therefore there is no way you could have actually premixed the oxidizing vapor into the liquid droplet. Okay, the liquid droplet is originally separate and then and as it vaporizes its fuel vapors mix at the flame. So it's essentially a diffusion flame. However, there are in certain liquid rockets, typically smaller ones, we use something called monopropellant liquids or liquid monopropellants, whichever way you want to call it, where the monopropellant, for example is a hydrogen peroxide, which can actually burn by itself because it contains both hydrogen and oxygen within itself, and as it thermally decomposes because of heating from a flame, it gives rise to both fuel and oxidizer gaseous species that can react at the flame, and that would be a premix flame, right. So except for this particular situation, we are essentially going to be looking at a liquid fuel droplet that is vaporizing and mixing with a gaseous oxidizing ambience at the flame, forming essentially a diffusion flame. And since we are going to be looking at a diffusion flame, we will actually look at what's happening at the Bergschröm limit, which is where the fuel and oxidizer vapors meet each other in the mixing field at stoichiometric proportions, and therefore locate the flame corresponding to where the stoichiometric surface is in the mixing field, similar to what we did for the Bergschröm flame. The general problem with most droplet combustion is to examine what is called as what is popularly called the d squared law. So the starting point for us to actually look at is what is called as the d squared law. What this really means is that there is a certain rate of evaporation or combustion of this droplet dictated by how the droplet diameter changes with time. Okay, so you now take a certain droplet of a certain diameter at a particular time and ignite it and get it to combust, or let's say it starts evaporating at a time t naught, then what this really means is, if you now start with a original diameter for the liquid droplet dl naught squared, and then the diameter decreases to dl squared at any time t, this is simply given by k times t minus t naught. This is what is called as the d squared law. Now this is an empirical observation to begin with, and certainly for many different droplets you don't necessarily have to have a d squared law. It could be d to the some power, which is approximately around 2. Okay, there are some situations where it could be as low as 1, sometimes and many times you don't necessarily fit in an integer for the power. It could be a non-integral number, like let's say 1.5, 1.8 and so on. Now on the face of it, what it really means is when you say d squared, it essentially refers to surface area. Okay, so what we can understand is more the surface area of the droplet, greater is the evaporation, right, and evaporation leads to combustion in a combusting environment, but whatever we are talking about will also be valid for evaporation when you have a hot ambience. So what we are talking about could be thought of even in a non-reacting sense, where you have a hot ambience. Okay, so like for example you want to dry a spray, for example, or dry droplets. Like for example, if you get hired by a washing machine company and you want to figure out how to design a dryer, like for example droplets that are actually trapped in a cloth, how they get dried, depending upon, of course you'll have to bring in convective heat transfer and so on. So you'll have to think about all the issues that we are talking about in that context. So whatever we are talking about now will also be valid for evaporation in a hotter ambience than the liquid droplet temperature. So and when we say d squared, it basically refers to surface area, and as a matter of fact the goal of atomization is to actually try to enormously increase the surface area of the liquid from originally, like let's say a flow of bulk liquid. You now want to actually spread the surface area for the given same volume, and essentially then increase the surface area so that you will now increase the evaporation and therefore the combustion rate and so on. So the goal of the theory here is to see if we can look at the governing equations and deduce the d squared law by applying the governing equations to this particular geometry and this problem. So obviously here dl naught is essentially dl at time t equals t naught, and t naught could be thought of as like a ignition delay beyond which the combustion begins, and k is what is called as the evaporation constant. Evaporation constant. So the framework here is we now assume that the droplet is spherical. It's not a bad assumption considering surface tension effects that try to keep the droplet spherical beyond below, I should say, below a certain size for a given droplet, given liquid. So this is not a very bad assumption at all. Like for example, if you're looking at droplets that are of the order of 10 microns or even 100 microns, they are reasonably spherical even in a gravitational field like what we face on Earth. And then so this is the fuel, and then what we expect is then there must be a concentric flame around it. Now this is a questionable assumption in a gravitational field because buoyancy effects will induce a vertical convection upward and also distort the flame shape in a way that is pointed upwards, alright. And of course what we are looking at is a droplet to be stationary in a quiescent gaseous oxidizing ambience. Therefore we could now assume the spherical flame concentric to the droplet. If the droplet were to be moving, right, so that there is a motion for the droplet, then the motion can correspondingly induce a distortion in the flame shape relative to the spherical shape that we have assumed. So that is not to be considered in what we are assuming, what we are taking up, because we are saying it's quiescent ambience. So if you now have a concentric flame, and this is the droplet, right, then we can say that the mass flow rate of the fuel that is coming out of the surface of the droplet is minus d over dt 4 over 3 pi r L cubed rho d, where RL is the liquid. I should probably use different subscripts here, but I think it's a mix up of subscripts, well just keep it as RL. Okay, RL cubed and rho L, where RL is the liquid radius and rho L is the liquid density. And now in this of course the liquid density is not expected to change with time, and 4 by 3 pi is constant, therefore we can pull them out and then differentiate RL cubed with respect to time, and that's going to give you minus 4 pi RL squared rho L drL divided by dt. The negative sign is because as time increases R decreases, okay. So and then we want to have a positive mass flux that's coming out, therefore you throw in a negative sign to make that out. So what we now assume, of course here we have already mentioned, assume spherical symmetry. Not a great assumption for moving droplets or in a gravitational field or both. The other assumption that's going to be quite important and needs to be elaborated upon is what is called as a quasi-steady assumption. What that means is the droplet diameter does not significantly change when the droplet evaporates and the gaseous vapor moves away from the droplet up to the flame and mixes with the ambience to form the reaction. In other words, the typical time scale of convection and diffusion of the gaseous species is much smaller when compared to the typical time scale of reduction of the droplet size appreciably. Alright. So how do I understand that? The answer is essentially coming from the fact that the rho L could be significantly larger than the gaseous density. Okay. So you can have a factor of about 2 or 3, sorry I shouldn't say factor, sorry, order of magnitude by about 2 or 3, like the gaseous density is like of the order of 1 kilogram per meter cube, the liquid density could be of the order of 1000 kilogram per meter cube, right. So what? The answer is we need to look at mass conservation across the interface, right. So for a unit mass per volume of liquid to evaporate will now give rise to a much lower density, which means as the surface recedes inward, it's now going to put out gas that has to actually move radially outward at a significantly larger rate. So to give you an idea, correspondingly, if you now say that the gaseous velocity that's going to go out relative to our frame of reference centered at the droplet center, if that's of the order of, let's say, a few meters per second, right, then correspondingly the droplet rate of motion is going to be only a few millimeters per second, right. So because you now have to have this 3 orders magnitude, 2 to 3 orders magnitude disparity between the rate of regression of this droplet surface inward to the rate at which the gases would evolve out of the droplet. What this really means is a couple of things. One, first of all, the droplet regression sets up a convection. So while we would like to think that it is purely a diffusion problem, right, in fact when you think about it as a diffusion flame in the Berkshire limit, where we now adopt an infinite chemistry, mixed as burnt approach, flame sheet assumption and so on, where we don't have to worry about the chemistry and we will have to worry about the mixing. So we would like to think that this is purely a mixing problem, wherein the liquid vaporizes and the fuel vapor steps out of the liquid surface after the vaporization and is just sitting there to diffuse. No, it is not sitting there, it is actually flowing out because you have this regression, right. But the second point that is actually being made is this, which is the regression is so slow when compared to the rate at which the gases move away from the center with a velocity such that we can now think of a droplet of a given radius at any particular instant as a snapshot. That means you freeze frame your droplet and then say for this particular droplet diameter the gases are rather instantaneously moving out and diffusing with the oxidizing ambience, forming the stoichiometric surface and hence the flame, and then the heat is rather instantaneously moving back to this droplet of this particular size. So all this balance happening in the gaseous phase is rather instantaneous when compared to the droplet motion that we can freeze this picture, right. That is what is meant by quasi steady assumption. That means as far as the gaseous equilibrium is concerned, the mass balance and the energy balance, the species balance and the energy balance is concerned, we can essentially say it's steady state. We don't have to worry about any unsteadiness. So we now start with the Schwab-Zelewicz formulation. The Schwab-Zelewicz formulation has its 11 assumptions, including a steady state, right, which we just try to articulate now. So the Schwab-Zelewicz formulation is the operator L of beta equal to 0, where beta is the coupling function, and of course for n species that we have, we are supposed to have n plus 1 betas. Of course, sorry, for n species that we have n betas and 1 alpha, so you have n plus 1 equations. But if you noticed what we did earlier with the premix flame as well as the Berg-Schumann diffusion flame, where we adopted the Schwab-Zelewicz formulation earlier in this course, we now try to choose those particular alphas and betas in the Schwab-Zelewicz formulation that is the most pertinent to what we are doing, so we don't necessarily have to worry about n plus 1 equations, right. So here what we want to do, and this is actually the art of solving the problem. So take here beta equals the energy beta, which is should say identically beta t, which is equal to alpha t minus alpha O. Now I could have used alpha f to subtract from any of the other alphas including alpha t, or some other alpha, some other species alpha, right. So the choice of actually using alpha t and alpha O is because I want to actually keep track of the oxidizing ambient species, which is purely gaseous, alright, and then the temperature, because the temperature is very important, because the energy balance is the one that is actually giving rise to a heat feedback that vaporizes the droplet. So if you didn't factor in the heat feedback, you are not going to be able to vaporize the droplet. So you need to have the energy balance, number one. And the oxidizing species is taken because it's purely gaseous. I don't have any problem with it vaporizing, right. So alpha t minus alpha O is a good combination that I can think about, which will now translate to a T superscript naught to T integral Cp dt divided by let us say the reference Q, that is based on the heats of formation, plus YO divided by WO nu O, where of course O I should mention here, O refers to oxidizer in the ambience, right, and L of beta is basically divergence of rho v velocity beta minus rho d divergence beta equal to 0, right. This is something that we have written about 2 or 3 times now in solving different problems. In fact, for the premix flame problem, we had a one-dimensional formulation, so it didn't quite really matter, but it was essentially one-dimensional Cartesian. In the Berg-Schumann problem, when we adopted the Schwab-Zelewicz formulation, we wrote it for a 2-dimensional cylindrical polar coordinate system. It's now going to be back to a one-dimensional situation, because the only variation is going to be along the radius, right. So but we are going to adopt a spherical polar coordinate system, alright, in a one-dimensional sense, where the radial variation is the only thing that is considered, and in a spherical polar coordinate system of r, theta and phi, we are going to have to get rid of phi and theta variations, but still the r variation, the one-dimensional variation in r, is going to be in a spherical polar coordinate framework. Therefore in spherical polar coordinates, this can be written as we get d by dr of r squared rho v beta equal to d by dr of r squared rho d d beta by dr. okay. The r squared as a coefficient is special to the spherical polar coordinates here, and notice that we have a double derivative here whereas we have only a single derivative here, okay, and we are using ordinary derivative because r is the only independent variable now, so it is not necessarily a partial differential equation. Now we want to try to bring in this m dot, which will rope in our RL, which is the radius of the droplet at any particular time, to any radius. So R is going to vary from RL to infinity, alright, and m dot is going to be, m dot can be, by the way, m dot can be defined for any R, for the mass flux of the gas, but at the surface it has to match the liquid mass flux, right. So m dot is essentially rho v times 4 pi r squared. Small v of course is the radial component of gaseous velocity, right, and rho is the gaseous density, right, or the density of the gaseous mixture in your domain. The domain is now for the gas, and so it starts from r equals RL to r equals infinity. That is how it is going, and m dot is for any radius, and that has to be a constant in steady state, okay. What is it? That is really what we do not know. What we are basically looking for is what is the rate at which the droplet is evaporating. If I knew what is the rate at which the droplet is evaporating, I would know what is the rate at which the mass is coming out of the droplet surface, and I would know what is the rate at which mass is flowing at any point r in the gaseous field and up to the flame and beyond and so on, but that is what I do not know. In that sense this is actually similar to the premix flame problem, where what we are actually trying to find out is the rate at which the flame was propagating, right. We did not know what the rate at which the flame was propagating at, and that is what was setting up the convection, right. Here again the m dot, the mass flux, which is a constant right from the droplet radius to any other location r in the gaseous field, is the unknown, and that is related to the velocity v, which is setting up the convective field for the gaseous flow, right. So we want to make use of this, and therefore what we want to do is, so the point basically is, whenever you see a r squared rho v, right, immediately what you want to think is, can I throw in a 4 pi and then make it look like m dot and then utilize it to be a constant, and then I can pull it out and then take it to the other side, slip it into the derivative. You can do all these kinds of things. So this can now be written as d beta by dr is equal to d by dr of 4 pi r squared rho d divided by m dot times d beta by dr, okay. That looks better, and we will try to make it look even better by introducing a new dimensionless independent variable. So introduce dimensionless independent variable psi equal to m dot times r to infinity 4 pi r squared rho d to the negative dr to the negative 1 dr. Now what does that mean? You look at here, you have a 4 pi r squared rho d divided by m dot. So strictly speaking, of course we could take this m dot inside the integral because it's a constant, and what you're looking at is m dot divided by 4 pi r squared rho d. Okay, since r squared is actually showing up in the denominator, right, we now have to end up integrating from r to infinity, and that's the reason why we are taking up an alpha O, or you can put it the other way. I took an alpha O, therefore I want to actually look at the region between any r and infinity as a measure of r. Okay, so this is a inverse thing. As r keeps growing, my psi is going to decrease, because at infinity psi is going to go to 0. Okay, so this is actually trying to invert r, because r is showing up in the denominator here, r as 1 over r squared, right. Now these are some of the things that are puzzling about combustion theory, which is you come up with these what should I say, innovative ways of non-dimensionalization, which is not very apparent to a student who is not really well versed with mathematics, but that's the game. This mathematics is typically so complicated that we will have to come up with these innovative non-dimensionalization methods that will try to simplify the governing equation significantly. So if you now adopt this particular independent variable, then you now transform your equations in terms of psi as opposed to r, and the governing equation becomes d beta divided by d psi equal to minus d squared beta divided by d psi squared. So simple, because essentially all the, well, this is the only term that has a coefficient within the derivative, and that is simply being robbed off by the definition of psi, therefore that vanishes, and you simply have d squared beta by d psi squared with a negative sign. And so essentially this is d squared beta by d psi squared plus d beta by d psi is equal to 0, right. So this is a linear second order ordinary differential equation for which we know how to write the solution. The solution is beta equal to a plus b e to the minus psi. Now let's call this 1. In fact, this is where we are going to start doing the problem. As of now we have not really done anything, because the problem is always defined by the boundary conditions. Alright, so strictly speaking I have not really said from here on, when the mathematics started, that I am working on the droplet problem. Okay, so the droplet problem is going to show up only when we start applying the boundary conditions, right, and the boundary conditions need to be applied in order to evaluate the constants of integration a and b, which are coming up because we have just solved a second order equation. So we have two boundary conditions that need to be provided in order to solve for this, and keep in mind we don't quite know psi as well. It involves m dot, that is the unknown. Okay, so in that sense this is kind of like an eigenvalue problem, and as I said, it's very similar to the premix flame problem, where we did not know the propagation speed, and that was an eigenvalue in that problem. And in order to evaluate that, besides applying boundary conditions there, we also applied an interface condition between two regions, the preheat zone and the reaction zone, and the interface condition was the one that actually fetched us the eigenvalue, namely the flame speed. Here we will also have to have an interface condition at the liquid surface, which is now trying to say so much of evaporation is happening for so much heat that is being sent, right. So in addition to applying boundary conditions in the gaseous phase at r equals RL, which is the liquid surface, and R equals infinity, we will also have to supply an interface condition in order to evaluate the m dot. This is what we will try to do. So need boundary conditions for beta and psi, right. So the first boundary condition is, so you have to go back and see what is beta. Beta is alpha t minus alpha O. Alpha t is this, which pertains to energy balance, right, and alpha O is this, which pertains to YO, which is the mass fraction of oxidizer, right. So if you are now able to actually generate boundary conditions at R equals RL and R equals infinity for YO and temperature or energy balance, then we subtract the one from the other in order to find the boundary condition for beta. So this is the process that we are going to do. So as far as the species is concerned, what we know is that the oxidizer cannot penetrate the liquid surface, alright. Now this is something that need not necessarily be true, but the moment you now are able to suppose that you have a liquid droplet which is intact and it is going to produce gaseous fuel, means that the oxidizer doesn't really, the gaseous oxidizer does not penetrate the liquid, okay. Now there are more complicated situations where typically one of the products of combustion, so what is going to happen to the products of combustion? So you are going to have the products being formed at the flame, right, and just like how we thought about the flame as a flame sheet in the Berg-Schumann problem, and we tried to actually locate how the temperature profile and the product concentration profile would vary away from the flame on either side, and of course the fuel concentration, oxidizer concentration plunging in at the flame and so on. We could think about it like that. So what we would expect is, as the products are being formed at this flame, they are at a high concentration relative to the neighborhood, and therefore they would have a tendency to diffuse, right. So they would diffuse inward against the current in this case, as well as outward, right. When they diffuse in, and of course the temperature is also going to be at its peak at the flame, and it's going to come down, so it comes down on both sides, and while it goes out there, it's going to match the oxidizer temperature in the far field, but it's going to match the surface temperature of the liquid, which could be like the boiling point of the liquid, right. And then of course inside the droplet you could have a constant temperature if the droplet is too small, so thermal equilibrium must happen significantly, considering that liquid thermal conductivities are an order more than the gaseous thermal conductivity and so on. Or let us say if you have still a profile that is going in, but at the temperatures of boiling point of the liquid, the product could also condense into a liquid, okay. So examples of this are, for example, if you now think about aluminum, which is used widely in solid rockets, where you have a molten liquid aluminum droplet that is burning, vaporizing into vapor phase aluminum or aluminum vapor and mixing with oxidizing species. Of course in the solid rocket you don't really have atmospheric oxygen kind of thing, you have oxidizing species in the form of water and carbon dioxide and so on, which carry oxygen atoms in them, and they mix and then form a flame, and the product of combustion is Al2O3, right, and in gaseous state, because the temperatures are so high that it would be even higher than the vaporization temperature of Al2O3. So you form aluminum oxide vapor at the flame, which now tries to diffuse out from the flame radially inward and radially outward, and a little bit further out the temperatures are now lower enough for the Al2O3 vapor to condense into Al2O3 liquids. The vaporization temperature of Al2O3 is significantly higher than the melting point of aluminum. Therefore, as the Al2O3 is diffusing backwards or inwards, it's now going to begin to condense, and then as it comes down closer, it now starts reaching the aluminum droplet surface. Keep it aside. Look at another example. Let's think about things like methanol or ethanol droplets, right? And in this case, you could easily think about an oxidizing ambience made of just atmospheric oxygen, right, or pure oxygen or air, whatever, and then you have a flame, and the products of combustion are carbon dioxide and water, which try to diffuse. But as the water, one of the products, comes back diffusing in, it now condenses, because when methanol exists as methanol, it's quite volatile, right, so it can vaporize, but the temperatures for the combustion are so high, somewhere in here as the water vapor diffuses back in, it can condense, right, and then further in it now finds the surface of methanol. Now the difference between these two situations of aluminum combustion and methanol combustion is, in one case the product liquid that is condensed is immiscible with the parent molten aluminum fuel droplet, whereas in the case of methanol the product water that has got condensed is miscible with the reactant fuel in liquid form. So as the water actually comes back in, it starts mixing with water in liquid phase and effectively dilutes the fuel. So as the combustion continues to progress, you get to a point where you are less and less rich in methanol, and therefore as the so what effectively the flame is trying to do is not only vaporize the methanol but also tries to vaporize the water that is mixed with it. Beyond a point it is not getting enough methanol to burn, and so the flame is going to extinguish at a certain size of this droplet, including having a certain amount of methanol as a residue along with water, right. As opposed to that, if you now look at aluminum, since the aluminum oxide is immiscible in aluminum because of interface tension forces similar to surface tension effects, all the aluminum oxide that is coming in cannot really stick at different points, so they tend to actually accumulate to one side, and they form what's called as a oxide lobe, or on one side. It could be any side, because we are not really necessarily looking at effect of gravity here, right, so for very tiny droplets, so it could be on one side, and this is going to first of all spoil your spherical symmetry, right, but you could still assume cylindrical symmetry about the lobe center, right. So there is an axis, and then the flame is now going to assume a shape that is cylindrically symmetric or axisymmetric, and then as more and more combustion happens, the aluminum part shrinks and the oxide lobe grows, and so you now have towards the later part of combustion of the droplet, you have a smaller aluminum droplet and a larger lobe, and ultimately when all of the aluminum is burnt, the lobe closes and becomes a oxide droplet, right. So that is the final product. So in both the cases you get a liquid product, all right, but in one case it is contaminated by some of the fuel that has got quenched without the flame being able to sustain. In the other case you get this, and of course when you have an oxide lobe, and if you are now beginning to think about a flow field, it becomes unstable, and then it can start wobbling and so on. So this is actually in reality a lot more complicated problem. The point I am trying to make is there are these problems where we would expect either the oxide to come and collect to one side or penetrate in liquid form, okay, penetrate the surface in liquid form and mix, whereas that is not necessarily the case with oxygen, Okay, if that were the case, then even as the liquid fuel existed, the oxygen would begin to actually get dissolved in it, right. So the first thing that we have to adopt is that oxidizer cannot penetrate the droplet surface. Oxidizer cannot penetrate the droplet surface, that is rho v y naught minus rho d d y naught by dr at r equals RL equal to 0. This is to say that the oxygen or the oxidizer, the gaseous oxidizer, can diffuse only up to the point that the droplet surface vacates by convection. So rho v times 4 pi r squared is m dot, and that would be the same as this m dot, right. So as far as the gaseous convective effect is concerned, this is because of the space vacated by the droplet trying to regress in its surface. So the diffusion is trying to match the droplet regression, right. So the droplet regression in terms of convection of the oxidizing gaseous species is this, and this is the diffusion. So this basically states that the diffusion can happen just as much as the convection can allow it due to the droplet surface regression. So this is essentially the boundary condition here, and this is in terms of R, but we have adopted a non-dimensionless independent variable psi. So this basically means that this is similar to the flux boundary condition that we had seen when we were considering axial diffusion of the Birch-Schumann problem, by the way, right, quite similar there. And dyo divided by d psi at r equals psi equals psi l is equal to minus yo at psi equals psi l, which can simply be called as minus YOL, where YOL is the oxidizer concentration at the liquid droplet surface. What we expect is the oxidizer concentration to be in stoichiometric proportions with the fuel concentration at the flame, alright, and further decrease to a value YOL. In combustion you will have the situation where the oxidizer is getting consumed in the flame. In evaporation you don't worry about a flame, it is just the heating from the outside that is causing the evaporation, and you will still have a ambient gas trying to diffuse up to the droplet surface and hold a certain concentration there, right. So this essentially is the oxidizer concentration at the liquid droplet surface. We don't know it quite, but we may have to make an estimate. We will worry about these things as we try to plug in some numbers or typical values for these things as we go along, but right now the boundary condition needs to be formulated to describe the droplet combustion problem. So that's as far as one boundary of one component of alpha O, right. Then we have to worry about what happens to alpha T at R equals RL, corresponding ones at infinity, and so on. We construct these boundary conditions and the interface condition, plug them into the solution in order to find out m dot. That's essentially what we want to do. We'll do that tomorrow. you.